You ever get the feeling that the world is running on some kind of secret code? You know that everything from the food you eat to the air you breathe is all following a hidden set of rules? Well, you're right, it is. And that code is chemistry. So today, we're going to crack it wide open. Let's get into it. Just think about it for a second. What on earth connects a carton of milk that's been left out too long, an old bike that's getting rusty, and even the way your own body gets energy from your lunch? I mean, they seem totally unrelated, but they are all linked by one single fundamental process. And there it is. That's the secret. They are all chemical reactions. And all a chemical reaction is, really, is a process where the stuff you start with, the actual building blocks of it, they change their nature completely to become something brand new. We're not talking about a simple physical change, like ice melting into water. No, this is a deep, fundamental transformation. Okay, so if these amazing transformations are happening all around us, all the time, how do we even spot them? How do we know a reaction has actually happened? Well, just like any good detective, the first thing we need to do is learn how to spot the evidence, the telltale clues that a chemical change is going down. And here are the four main clues you're always going to be looking for. Did something change state in a weird way, like a solid suddenly producing a gas? Did the color completely shift? Are there bubbles appearing out of nowhere? Or does the whole thing suddenly feel way hotter or colder to the touch? Any one of these is a dead giveaway that a reaction is happening. Now, check this out. This is a great example because we're actually seeing two of those clues at the same time. When you drop some dilute acid onto these little zinc granules, you immediately see gas evolving. Yep, those are bubbles of hydrogen fizzing up. But also, if you could touch that flask, you'd feel it getting warmer. That's a clear change in temperature. It's a classic chemical reaction, caught in the act. Okay, so we're getting good at spotting a reaction. But a detective can't just see the clues, right? They have to write them down, record their findings accurately. So that's our next step, learning to speak and write the universal language of chemistry so we can describe these reactions with total precision. And this quote it nails it. Simply observing that, it made bubbles isn't really science. Science is about organizing those facts into a meaningful, structured language. We need more than just a list of observations. We need the actual literature of equations. And here's why that matters. Trying to describe a reaction with a full sentence like this is, well, it's just clunky. It's long, it's inefficient, and honestly, it's not very scientific. There's a much better way. So the first step to cleaning this up is to use a word equation. See? Much clearer. On the left side, you've got your starting materials. We call those the reactants. On the right, you've got what you end up with. That's the product. And that arrow in the middle, it just means turns into. Simple, clean, and effective. But this is the secret code itself. When we use chemical symbols, we create a chemical equation. It's super concise, it's universal, and it tells us exactly which atoms are in the game. This is the elegant shorthand that scientists all over the world use to communicate perfectly with each other. Now, every secret code has its rules, right? And chemistry has one golden rule, one law that can never, ever be broken. It governs every single chemical reaction in the entire universe. And if you can understand this, you're on your way to mastering the language. And here it is, the law of conservation of mass. What this really means, in simple terms, is that you can't just create atoms out of thin air and you can't make them disappear. You can only rearrange them. So the number of atoms of each element you start with has to be the exact same number you end with. Everything has to be accounted for, no exceptions. Uh-oh. Okay, let's apply that golden rule to our magnesium equation. We start with one magnesium atom, we end with one. Great. But we start with two oxygen atoms, and we end up with only one. So where did the other one go? Right now, our code isn't telling the truth. It's what we call an unbalanced or a skeletal equation. We have to fix it. And this is where we really become code breakers. Balancing an equation is just the process of making it follow that golden rule, the law of conservation of mass. Think of it like a puzzle, and once you know the steps, you can solve any of them. So let's try a trickier one to really see how it's done. So we're going to look at iron reacting with steam, and there's a really simple method. First, you just count up all the atoms on both sides. Then, you find the element that's in the biggest bunch, in this case it's the oxygen, and you balance that first. Then, you just work your way down the list until everything matches. That last step, the final check, is absolutely crucial to make sure you didn't miss anything. And this table just lays the problem out for us perfectly. Look at those numbers. We've got 1 iron on the left, but 3 on the right, 1 oxygen on the left, 4 on the right. Only the hydrogen is balanced right now. So yeah, we've definitely got some work to do. And voila! By adding these big numbers in front, we call them coefficients, we've cracked the code. Now let's count them up. 3 iron on the left, 3 on the right. Check. 8 hydrogen on the left, 8 on the right. Check. 4 oxygen on the left, 4 on the right. Check. It is perfectly balanced. Now it tells the true story of what's happening. All right, so now that we can read and write the code, we can start to see the bigger picture. It's like a detective who's learned to recognize different types of crimes. A chemist learns to recognize different types of reactions. And you start to see these common patterns showing up over and over again. Let's start with two of the big ones, and they're basically opposites. A combination reaction is, well, it's exactly what it sounds like. Two or more things combine to make one more complex thing. A decomposition reaction is the reverse. One complex thing breaks down into two or more simpler things. They're just two sides of the same chemical coin. Here's a perfect example of combination. You take some calcium oxide, also known as quicklime, and you add it to water. Those two separate things, A and B, combine to form just one single new product, calcium hydroxide. And you get another clue with this one. It releases a ton of heat. The beaker actually gets hot. We call that an exothermic reaction. And now for the opposite. If you take these green ferrous sulfate crystals and you heat them up, something really cool happens. That one single starting material breaks apart. It decomposes into three different, simpler products. You can actually see the color change, and you can definitely smell the sulfur gases. It's a textbook decomposition. And there you have it. Think about the journey we just went on. We learned how to spot the clues that a reaction is happening, then how to write the secret code of chemical equations, and finally, how to identify the basic case types. You've really learned the fundamentals of being a chemical detective. But here's the most important thing to take away from all this. This isn't just theory for a test. This language describes the real world. The next time you cook an egg, or see a firework, or even just take a breath, you can see past the surface and understand the elegant atomic dance that's really going on. This code is literally everywhere. So what are you going to use it to discover next?